Good morning, everybody. My name is Max Scardelletti. I'm from NASA Glenn Research Center. Today I'll be presenting a paper on package compression and pressure sensor systems for aircraft engine health monitoring. So what we're trying to develop is sensing systems for harsh environments such as aircraft engines. And there's three major industries that kind of have a big say in this. And the first one is the downhole oil and gas industry, where they currently have sensors about 150 or 150 C or 175 C, but that's going to change because they're starting to do access wells that are a little harder to get to. So we have electronics that approximately go to about 300 degrees C. Also have the automobile industry, which is loaded with sensors and electronics that you can see cylinder pressure temperatures about 300 degrees C. And also exhaust sensing temperatures can be as high as 850 C. And then you have aerospace. And monitoring the health of aircraft engines at temperatures above 300 degrees C is what we're really looking trying to make a big stride in. And these sensors could be part of emissions, temperature, blade tip clearance, and pressure, of course. And also we're working on landers for Venus. And so the atmospheric and surface conditions on Venus are about 480. So the scope of this work is to develop a SiC-based MEMS capacitive pressure sensor system that can be used to monitor pressure on a conventional gas turbine fan engine. And our operating conditions, we have a temperature, we need to operate about from 25 to 500 degrees C. We have a pressure range of 0 to 300 PSI, and we have to be able to withstand vibration up to 5.3 GRMS. The system realized by integrating the following components on a common high temperature substrate. We chose alumina. Alumina's substrate that we like to use. We use Coors Tech Superstrates 99.6. We have a novel SiC and the silicon carbide nitride MEMS capacitive pressure sensor. We use silicon carbide MESFET as the active device. We have MIM capacitors, wirewound inductors, thick film resistors. We have low form packaging, and a borescope plug adapter, which I'll explain a little bit more, which will be used to integrate to the engine. Now, on this design that we chose here was a Clapp-type oscillator. And as you can see, here's the LC tank circuit. Oh, I think I closed it. Oh, there it is. Okay. Sorry. Yeah. Okay. So as you can see, this is the integrated. This is the LC tank circuit of the device, and that's where the capacitive pressure sensor is. And the integrated system uses a Clapp-type oscillator with capacitive pressure sensor located in the LC tank circuit. As pressure increases on this system, the pressure sensor capacitance decreases, what causes the operational frequency to increase. And once again, we use a Cree SiC MESFET to drive the circuit into oscillation. And on this schematic, you could also see the biasing circuits for the drain and for the gate. So why do we choose the Clapp versus the cold pits? Well, we're going on an engine. So the proposed Clapp oscillator requires one inductor, 3 capacitors, and 1 MESFET. Requires few components than a typical cold pits oscillator design. This increases system efficiency as well as increases system reliability under harsh environment conditions, especially temperature and vibration. So once again, LT and C-Sense are in series, and C-Sense is used to set the operational frequency, and that leaves C1 and C2, which can be used to control the gain conditions. So it kind of separates the two. This arrangement increases frequency stability, making it more frequent stable for this operation than the cold pits. So first thing we needed to do is we need to determine the capacitance of our pressure sensor. So we developed the system at NASA, and there's the system. It has a pressure range, this one, of 0 to 100 PSI. Temperature good to 25 to 500 degrees C. We use a LabVIEW program to control the power, which controls the heat. We have a power source, multiple thermocouples throughout, multiple feed-throughs throughout, and a sight glass for signal transmission in the event that we would go wireless. Okay, so this is a look at the Sporian SiCN capacitive pressure sensor. Now this is as you can see here, it's like I said, silicon nitride carbide capacitive pressure sensor. This is the sealed cavity. This is the aluminum substrate, and then we have gold feed lines to make connection. It's a parallel plate capacitor model. The SiC, it's a SiCN membrane, and the temperature on this sensor is good up to 1,000 degrees, and the pressure range on this sensor is 0 to 400 psi. So what we did is we took a shot, we loaded it up in our chamber, and we did at room temperature. We just wanted to see what the difference in capacitance would be. And as you can see over here at 0 psi, we had a capacitor of 3.84 picofarads. At 50 psi, we had a capacitor of 3.6 picofarads. And at 100 psi, we had a capacitor of 3.3 picofarads. So as that capacitive increases or decreases as a function of pressure, that will increase the resonant frequency of the Clapp-type oscillator. So now the first thing we're going to do is we're going to model this in ADS. I like to use Acknowledgements, or now Keysight actually it's called, Advanced Design System Software. It's a circuit simulator. And these are the values for what we have chose to reach our operational frequency of about 100 megahertz, 96.7. And once again, we use a Cree MESFET model in ADS, which is pretty accurate for this design. And as you can see C2, the sensor capacitance. This is our tank circuit inductance. Then we have C1, C2, which control the gain again. And then these are our DC bias. So first thing we look is at a harmonic balance and make sure it's operating properly. And as you can see, it does operate at 96.7 megahertz. That's the first harmonic. And then all the subsequent harmonics afterwards. And then to show a little bit, to further gain stability, we like to see a phase, a zero crossing or 180 crossing at the operational frequency of 96.7 megahertz, which you can see there. And then also we want to see on the loop gain, we want to see a unity greater than unity at the operational frequency, which once again you can see that it is. So this tells a little bit more that it's a little stable, and it shouldn't destabilize or stop oscillating for some certain other reason. Now, what we did though is we took the three capacitances that we went on the pressure sensor, and we wanted to see how it affected by putting those three different capacitance sensors of the pressure sensor into the simulation. And as you can see at 0 psi, at 3.84 picofarads, the operational frequency was 96.7 megahertz. So then we went to the 50 psi with a capacity of 3.6 picofarads. As you can see, we moved up to 99.2 megahertz. And as we increased the pressure, or at the pressure of 100 psi, which gave us a 3.3 picofarad capacitance, the operational frequency of the Clapp-type oscillator now at 102.8. So we can see that it's working the way we want it to work. Okay, so now we want this is not wireless. This is a packaged wired prototype, which has the following characteristics. The unpackaged sensor system, the size is roughly, we had to keep it about 8 by 40 by 4 millimeters cubed, and that is including everything on-chip sensor, all circuit, and DC bias as well. The form factor, packaged sensor is equipped with borescope adapter for a borescope plug on the engine, which I'll show you shortly. A maximum operating temperature is 500 degrees C for 1 hour at the tip of the borescope adapter, and that would be right at the engine interface. And then also, we have to have maximum vibration of 5.3 GRMS, and it's got to be along the X, Y, and Z axis for at least 20 minutes on each axis to prove that it won't fall apart when it goes on the engine. So this is a photo of the entire circuit, all on chip. And as you can see, the outputs, for the output, the drain, the source, the gate, this is 6 millimeters by 35 millimeters. It's approximately 2 millimeters high. There's the pressure sensor system. This is for the drain biasing. Here is the thin film resistor for the gate biasing. There's C1, C2. We have a Cree MESFET right there. And there are two wirewound inductors in series with the pressure sensor. All on aluminum chip. So now we need to package this because we have to set it up so that it actually positioned on an engine. So we made a stainless steel package. We have thermocouples in and throughout the packaging. Some connector cable from the package to facilitate input, power, and output signals. And then we have the borescope adapter. And that is right here. This is the borescope adapter right here. This sleeve, here are the electronics. This is a metal packaging where we had the big connector, which it's hard to see it right there. And this sleeve slides over this. And at the tip of this sleeve, it's a roughly, we say about 500 degrees C when it's at that engine point. Okay, now to test this setup, to test this packaged rig, we had to make a little test fixture that could withstand the pressure and the temperature. And then we'll slide that into the oven. So we built a custom in-house pressurized fixture. The package sensor is attached to the quasi-borescope adapter, which again is this piece right here. Now the electronics are right in here. This is where they're at. And the thermocouple inside the test fixture to emulate inner engine temperature. So we had a thermocouple positioned right in here. You can barely see the wires coming out the back end, but that's where the thermocouple would be. So to test that, we had to test it in the tube furnace. So this is our benchtop package system characterization. Control jet turbofan engine conditions. The package sensor was heated to over 500 degrees C, and the pressure was increased from 0 to 300 psi. But you got to note that roughly right here, where the electronics are at, we have a thermocouple there, and that's roughly 400 degrees C. So the tip of it is at 500, which makes the acceptance level testing for the engine itself. So when we actually go to the Air Force to put this in the plane, we can say that we actually hit 500, but back here, just off a few inches, or not even an inch, is roughly 400 degrees C. And we claim that's a steady state temperature of the system. Okay, so now this is again benchtop testing. So down, now we're at the tube furnace, and that tube furnace actually 500 degrees C. It actually goes up to 400 psi, but we're going to take it that high. We're only going to 350 just to prove acceptance testing for this package system. And so as you can see, there's more. So how I tested this was on a spectrum analyzer and power sources and pulled out data. So as you can see, at 0 psi, we're at 96.8. At 100 psi, 200 psi. At 300 psi, we're at 116.7 megahertz. 350 psi, we're at 119.86. Keep in mind, the simulated and measured response at 0 and 100 psi are virtually identical to the circuit model that I showed you previously. So that just shows you the accuracy of that model. So now we could take that model, which we did do, and further extend it out to 500 degrees C just to see, or 350 psi to see where we stood. And it was extremely accurate. And also we were able to pull the capacitance of the pressure sensor, extend that out to 350 psi, and I'll show that. Works very well, lines right up with the measured data. And then here's the actual measured output at 0, 100, 200, 300, and 350 psi. These are all the spectrum peaks that you would see. The spectrum response of the package from 0 to 350 psi, and all that room temperature right now. So now the next thing we need to do is we need to characterize it at temperature and pressure. This is part of the acceptance level testing for Pratt & Whitney and the Air Force. So the temperature at the tip of the sensor inside pressurized fixture is 540 degrees C. It's a little more difficult to control the temperature on this setup than it was on the smaller temperature rig that we measured the pressure sensor with. So all the temperatures will be up there. The change difference is at 25 and 500 degrees C at 0 psi is less than 1%. So what that's telling you is that 0 psi, 96.3 megahertz, off slightly, 320 psi, because once again, we couldn't get to exactly 350. It's 117.8 megahertz, which gives us a sensitivity of 6.8 times 10 to the negative 2 megahertz per psi. And that's a percent difference of 20%. So it's very sensitive. I mean, we could carry it over a long range, and it still seems to work over that frequency range. So now the next thing we need to do is we need to test vibration. So what we did at NASA Glenn, we have it's called our structural dynamic testing lab. Basically, we have several vibration tables, and we make test fixtures, sensor, or whatever we're testing for each individual sensor that we're going to test. And in this one, there's the test fixture for our sensor. And then there is our sensor there. So to emulate engine testing, we did sine wave sweeps. We do random vibration sweeps. We have a maximum vibration of 5.3 GRMS. We are testing in the X, Y, and Z testing axes. And the resonant frequency was recorded at the beginning and the end of each test with no change. So instead of showing you a bunch of more screens of spectrum response, you could basically, we started it at the beginning, ran it through the whole vibration test, seen that it worked, and we knew that everything was. This is a 1.4G sinusoidal sweep profile. This is the output that we would see coming from the way they recorded the data in the structural lab, the structural dynamic lab. And then this is also for the 5.0 GRMS random vibration profile, the typical profile. Once again, after all the testing, there was just too much data really to put up, so we just give you kind of an idea of what we're kind of looking at here. Now, once we went through the structural, I always take it back into the pressure and to the temperature, because the structural was the toughest test for that pressure sensor to make it through. So I want to make sure it's still working properly. So I put it back on the back in the tube furnace again in that custom fixture, and the package temperature system was again measured after structural dynamic at 0 psi at 25 degrees C. You can see the temperature was 97.3 megahertz of frequency. At 0 psi at 520 degrees C, it was 96.5 megahertz. And then at 342 psi and 520 degrees C, it's 118.1 megahertz. But the big thing to note here is the change in frequency at 540 C at 0 psi is less than, at 25 and 0 psi, is less than 1%. So as this thing was increased, and once again, we believe it's about 400 degrees C, there wasn't really no change in resonant frequency with all those components, which kind of tells us this is working very, very, very well. So now we know we passed acceptance level testing, both in vibration and also in temperature and pressure. So now we're off to Edwards Air Force Base to test it on a Boeing C-17 Global Master III. And the engine that we're going on is actually a Pratt & Whitney F-117 turbofan engine. This is all part of Viper. And Viper is Vehicle Integrated Propulsion Research Project. This is actually Viper 3, the name of this project. And Viper was a series of ground-based on-wing engine demonstrations to mature aircraft engine health management technologies. Once again, the test vehicle was a U.S. Air Force C-17, and the engine was a Pratt & Whitney F-117. And Viper partners include, well, NASA, all of NASA, U.S. Air Force, Pratt & Whitney, GE, Rolls-Royce, Boeing, FAA, USGS, and there was other agencies as well. This was an extremely expensive program, and many, many parts. So part of Viper, once again, was to put, we had sensors, different type of sensors, and monitoring the engine at faults and things like that over over days of testing. So what we wanted to do is demonstrate the capability of advanced health management technologies for detecting and diagnosing and engine faults before they become safety impact to minimize loss of capability. And the approach was to perform on-wing engine tests, normal engine conditions, then some seated faults, seated gas pass faults, accelerator engine life degradation, and then the big thing what this was all about, once we calibrated, and this was basically our calibration, then we go to volcanic ash. And we test for volcanic ash being ingested into that Pratt & Whitney, see how it affects it, because that's what this entire project was basically about, to determine the effects of volcanic ash and kind of approach, or what is a safe distance, or what a level of volcanic ash actually going into the engine gets to a point where it will degrade enough so that the engine has a problem and we could crash. Because actually, once there's an eruption, the aircrafts have to fly hundreds of miles away from volcanic ash because of the damage that it does. We have self-diagnostic accelerometer. We have this is a microwave clearance sensor, fiber optic sensors, emissions. thin film sensors, and of course we have the pressure sensor. So on this, this is a layout of the plane. So this is looking in the C-17, but you can see all the different stands. This was the rack. This is where all the data went to over here. This is the cockpit over here. And then we were positioned this table right there. So this is a look at the inside of the aircraft. When you're looking in, in the cockpit would be behind you. Once again, this is what we called the rack. That's where all the data was sent to. And then our system, we are way back there. And if you take a look at this one, that's our spot right there where we were positioned. So we have all our test equipment on the bench here. We have wires that come out, that come up here, they go through the fuselage into the wing and down into the actual engine where the sensor is actually positioned on the engine. This is just a quick setup to show you kind of just a drawing to show exactly what I had on there. So in the fuselage, I have my spectrum analyzer. We got a laptop, LabVIEW program to record the measurements. And that was 200 foot of cable that we actually had to go from my station out into the wing. And that's just a quick little drawing of that. Now this is what the data I will be showing you now. So this is what the actual engine kind of looks like. This is a cut of it, and you've seen this several times already. But this is P25, or P25, AP7 and PS3. These are two pressure devices that are on the engine right now. So we're going to record our pressure, and we have this recorded pressure to see how they compare to the two. And remember, high temperature capacitive pressure sensor is at AP7 in the gas flow path right there. Okay, so now once again, to get actually like an idea how the engine is running, some baseline engine tests. The crew would come to the plane in the cockpit, we would go over this every meeting. And then this test, we call this a baseline engine test profile. As you can see, the pilot will be at RPM, will be at idle, then he revs it, go to max RPM, and then he breaks it down so many percentages each. We get down to the bottom, we do this ramp up, and then we do a quick snap. So then if you look at this, you can see the output data, and this is time in seconds versus pressure, and this is all normalized. You can see P25 is here, and you can see how it kind of goes down a little bit. You can see those. PS3, you can see how it tracks the engine performance, and then you see Sporian, and we're kind of in the middle. So that means that the pressure was somewhere in the middle of P25 and PS3 at that position in the gas path on that engine. That was the baseline run. Then we did a transient run, which basically a transient run is basically just a ramp up, keep it idle for so much time, and back down to idle. And as you can see over here, once again, you can see how we track that. And then the last type of run we did was a steady state, which is exactly what it looks like. Idle, get up to a steady state run, and then bring it back down. As you can see, P25, Sporian, and then PS3. So that was the health. Now that was just to get a baseline of everything. That was what this whole test was about, to figure out, okay, how are sensors acting as a function of pressure and temperature on that engine. So now we got kind of an idea. So now we want to run volcanic ash. So this is the whole thing was all about, once again, was volcanic ash testing, because once again, they want to see how that affects what amount, where is the safety line, how many miles away would they have to be, according to what flow of ash would be okay for a plane to fly through. And we did 5 days of ash testing. The first day was at a very low rate, was at, the total of the low rate ash testing was 14 hours. And as you can see, it was 1 milligram cubic meter. And this one, unfortunately, P25 on the aircraft, on the actual engine, didn't work. So we had to move on. We left that one out. And as you can see how we tracked it. So basically, all we're doing here is no more baseline test, no ramp, no snap, anything like that. We're just getting in the engine, or getting the pilot is just bringing the engine to an idle somewhere, some steady state line, and or some percentage of RPM, and we're just going to run it. We're just the ash flowing in. So this was the first day. The second day looked just like this. It was the same thing, no change, which is, we didn't see anything. And then, unfortunately, on this one, on my sensor, we started having failure on the third day and the last day of volcanic ash. It was getting right towards the end of the day when we were going to stop it. But what we noticed was that the cable actually on side of the engine started to break apart. But when we brought the sensor back home, back to NASA, and we tested it, we were able to test it and get more data from it as well. But unfortunately, the bad thing is once that started, then we couldn't go into the heavy flow ash rates. And so I missed out on that data, which when if you were to look at that, then you would have actually seen the degradation. And it started, like on the other sensors, you would see they started degrading. And the engine really started to fail, and that's when they had all their, that's when they had issues. And so that's what they wanted to do, is burn up the engine. So that's as far as we made it. In summary, basically, we developed a Clapp-type oscillator concept. We developed a package, pressure sensor system. We demonstrated the accuracy of simulations and measured data. We performed pressure, temperature, and vibration acceptance testing. And then we successfully demonstrated the sensor system tracking engine performance on the engine. And some acknowledgements is some of the people that also, there was a lot of people who worked on this project, but people that were invested a lot of time in this pressure sensor system were from NASA Glenn Research Center, and then also Sporing Microsystems, which provided the sensors for us. And that's it. Thank you.